Today we're going to take a look at some typical cases where we've got problem solving in circular motion. I said many times earlier in the course that the most common thing we do in this course is a two-stage process where we draw a free body diagram, and then secondly we write an equation based on the idea that the net force on a body must equal the mass times acceleration. Or we might say that the sum of the real forces acting on a body, the vector sum, will equal the mass times the acceleration. And we do exactly the same thing here with circular motion. So we got some object moving around in a circle. Let's say it's over here. Then at any instant in time, we can draw a free body diagram. And so we might have a bunch of forces acting on that object, maybe something like this. But what we know is that if we sum up all those forces, we have to get a net force towards the center of the circle. And we also know that at any time, that net force has to equal mass times velocity squared all over the radius of that circular motion. So this ma here is going to be replaced by mv squared over r. Now, don't get worried that we're going to have a whole bunch of vector forces to add up here. In typical cases, we'll only have one or two forces producing that net force towards the center. So now let's use this process to solve this problem involving Tarzan here. So we've got Tarzan swinging on a vine, and we're trying to find out whether or not the vine's going to break when he's right at the bottom of the swing. And we choose the bottom of the swing because that's going to make everything a lot simpler. So my first step is to draw a free body diagram. So here is Tarzan at the bottom of the swing. There's two forces acting on him. Of course, on all objects, there's a weight acting downwards. And in this case, there's also a contact force because he's in contact with the rope, and the rope is pulling him upwards. We'll call that a tension force. And you'll notice here I drew the tension force to be bigger than the weight. Now, how did I know to draw the tension force bigger than the weight? Well, we know Tarzan here is doing circular motion. And if he's doing circular motion, the centripetal force, the net force, the resultant force, has to be towards the center of the circle. So this has to be F net. So the magnitude of that net force has got to be equal to T minus mg. So now let's go down and set up our equation. So we can either write F net equals ma, or we might write that the sum of those real forces acting on the object must equal to the mass times the acceleration. Well, we said when it's circular motion, the acceleration is v squared over r. And this net force, or the sum of the real forces, that's this T minus mg. So we've got an equation here. T minus mg must be equal to mv squared over r. Now I'm trying to find out if the tension is bigger or less than 1200 newtons. So what I'm going to do is rearrange this equation for the tension. The tension must equal the weight of the object, so the rope has to support his weight, plus this mv squared over r, the net force. In other words, not only does the tension have to lift him up, support his weight, it's also got to make him turn in a circle. So now I can simply substitute in my values for the mass and the speed and the radius. The mass was 80. Take g to be 10 for simplicity. Mass here is 80. The speed was that 8 meters per second, and that'll get squared. And the radius here was 10 meters. And notice here all the numbers are MKS units, so I don't have to do any conversions. So it takes 800 newtons to support his weight, plus another 512 newtons to make him go around the circle. So the tension in the rope is going to be 1312 newtons, which is bigger than 1200 newtons, the braking strength. And therefore we know this is going to break. So let's see if you got this idea. We have an IB multiple choice question, very similar to the Tarzan problem, except you're going to have to use conservation of energy here. So pause the video, try the question, come back for the solution. Let's start with our free body diagram. It doesn't change from Tarzan. We've got mg going down, we've got the tension pulling upwards, and that means that the tension minus mg, that net force, must be equal to mv squared over r. Exactly the same as Tarzan. We can rearrange that. The tension has to equal to the weight of the object plus that force needed to pull the object around in a circle. Now at this point we have an answer for our tension, but it doesn't agree with any of the multiple choice answers, so we're going to have to express this in a different form. And we're going to use conservation of energy to do that. This mass here, it drops through a distance equal to 1 radius. So its loss in gravitational potential energy will be mg times that drop distance. And all of that loss in gravitational potential energy gets picked up as kinetic energy, a half mv squared. So now we can rearrange for mv squared over r. It's just going to be equal to 2 mg r over r. R's will cancel out, and we get that mv squared over r is the same as 2 mg. So let's make that substitution. We get T equals mg plus 2 mg, which is 3 mg. So the correct answer is D. So we've gone over this Tarzan situation where we started with a free body diagram and then we wrote F net equals ma and came up with an equation like this. Here's a number of other situations that are very, very similar. And I'd like you to work through the same process, do the free body diagram, and then come up with an equation that represents F net equals ma. So the situations are a bump in the road with a circular shape, a downwards bump in the road with a circular shape, a vertical circle, so this might be a mass on a string that's being swung around in a vertical circle, an airplane loop, so we're talking about an airplane doing a loop-to-loop. It's at the top of that loop and the pilot is downwards, so we'd like an equation that's involving the normal force downwards from the seat of the plane on the pilot. And finally a hoop, so this might be a Hot Wheel set. Hot Wheels are small toy cars that move around on plastic tracks. So here we've got a toy car at the top of this hoop of plastic track. So pause the video, see if you can repeat these two steps for each of these different scenarios. Okay, bump on the road. Well, we've got mg downwards. In fact, we can draw mg downwards the same for all of these. Mg downwards is everything has a weight. Then we look for the contact forces. The contact here is with the surface, of course, so we're going to have a normal force up. The normal force won't be as big as mg. Mg's got to be bigger, so we get a net force towards the center. So our equation is going to be mg minus n equals mv squared over r. Next situation, once again, we're going to have an upwards normal force from this surface, but this time the normal force is going to be bigger than mg because the net force has to point towards the center of the circle. So this time we're going to get n minus mg, that's the magnitude of the net force, equals mv squared over r. Next situation, the contact force is going to be with the rope itself, so it'll be a tension force that also pulls towards the center of the circle. So these two forces pull together in the same direction, and the magnitude is going to be T plus mg. That's got to equal mv squared over r. Once again, these two forces, mg and the normal force from the seat, have to be in the same direction, so we just add those up. N plus mg equals mv squared over r. And in this one, the normal force is downwards from the railing. We'll call that n. So n and mg are once again in the same direction. We've got to add those two forces up to get the magnitude of the net force, and that's towards the center of the circle and equal to mass times acceleration. So you might notice here that these three are mathematically the same. Okay, let's take this a little deeper. And what we're going to do is analyze what happens when an object goes over a circular bump. So here's our circular bump. And we'll say it's got a radius here of r. Here's our object going over the top with a speed of v. We draw our free body diagram. The weight is the bigger force because the net force is down, and the normal force from the surface is up. So our equation, mg minus n equals mv squared over r. So let's say we now speed our object up a little bit, so v is a little higher. Well, of course, mg doesn't change. mg is the same. The weight doesn't change. But this mv squared over r is going to be bigger, which means that the normal force here is going to have to be smaller, so that we're taking mg, subtracting something smaller, and so we're getting something bigger over here. And then suppose we keep speeding it up. Then eventually that normal force is going to get smaller and smaller and smaller. Eventually the normal force will be 0. So our equation would be that mg minus 0 equals mv squared over r. Now at this point we might solve for v. We could say that mg must be equal to mv squared over r. M's would cancel out, and we'd get that v is equal to the square root of rg. We'd probably call this here the critical speed, the speed at which there's 0 normal force. What that means physically is that the object here is just kind of gliding over the top of the bump here. It's not quite touching the bump, and it's following this circle perfectly. And mg, the weight of the object, is providing all of that turning force, all of that centripetal force. Now let's suppose we go even faster. Now it's not like we can get a normal force that's negative or anything like that. Our normal force will still be 0. Our weight can't change, but we've made our speed bigger. So the only way that we're going to be able to get this term on the other side for the centripetal force to be equal to the same mg is if we now get a much bigger radius. In other words, if we go faster, if our object here lifts off and goes in a bigger radius circle. So the radius becomes bigger, the object lifts off the bump if we try to go any faster than that critical speed. Now there's one other idea that I want to go over with you. We have this formula for the net force, or the centripetal force, mv squared over r. But oftentimes we'll have something in circular motion, like say the Earth around the Sun. In that case, we usually don't know the speed of the Earth around the Sun, but we know it takes 365 days for the Earth to go around the Sun. So we know the period, but not the speed. So it's sometimes advantageous to write this equation in terms of the period or the frequency. So let's see how we would do that. So we've got circular motion, we've got a speed v, we've got a radius r. And of course the speed has to equal distance over time. So if we imagine our object going around the circle one time, then the distance here would be the circumference of the circle. It would be 2 pi r. And the time it would take is what's defined as 1 period, the time to go around once. So our speed would be equal to 2 pi r divided by t. So we can make that substitution. We're just going to square this, 2 pi r divided by t, square that. We've still got an r down here, so we're going to get m times 4 pi squared r squared divided by r times t squared. And we get this expression for the net force, or the centripetal force, which is that 4 pi squared times the mass times the radius divided by the period squared is equal to the centripetal force. Now, of course, period is equal to 1 over frequency. If it takes 2 seconds to go around once, then you're doing half a revolution every second. Period and frequency are reciprocals of one another. So we can also write the net force, the centripetal force, as 4 pi squared mr times the frequency squared. In other words, if I write t squared as 1 over f squared, the f comes up into the numerator. So let's try an application where we use this equation that the net force for circular motion, or the centripetal force, is given by 4 pi squared mr all over the period squared. So pause the video, try the question, come back for the answer. So if this is the Earth and this is our person on the equator, then that person's moving in a circular motion with a radius equal to the radius of the Earth. So all we really need to do here is plug into our equation. It's 4 pi squared. The mass is 80 kilograms. That's for the person. The radius is the radius of the Earth. 6.4 times 10 to the 6th. And the period, we need to be a bit careful with that because we need to use MKS or SI units. So we're going to get a force here in newtons. That means we've got to convert 24 hours into seconds. And there's 3,600 seconds in 1 hour. So we need to multiply by 3,600 and then squared. If we carry that out, we get an answer of 2.7 newtons, or roughly 3 newtons. Now this kind of has an interesting meaning, because let's suppose we put our person here on a weighing scale, and we do our free body diagram. Of course, we'd have a force towards the center of the circle equal to the weight mg, and then we'd have that normal reaction force. I've used R, I'm going to use N for newtons, so I'm going to use a C here called a contact force pushing upwards from the surface of the Earth. So the net force would be mg minus c. Mg's got to be bigger because the net force has to point towards the center of the circle. So mg minus this normal force or contact force has to be equal to the net force for circular motion, this 3 newtons here. Now mg, that's just the person's weight. That would be the 80 kilograms times 9.8 newtons per kilogram minus that contact force gives us 3 newtons. We can solve for the contact force. It's going to be 784 for the weight minus 3 for the needed net force. So our contact force, our normal force, is going to be 781 newtons. So the true weight of the person is 784. The contact force is only 781. And you'll remember in our discussion of scales earlier that the reading on a scale is the normal force. So when you get on a scale, the reading is always a little bit less by a few newtons than your true weight. And that's due to the rotation of the Earth. So let's summarize the key ideas from the video. Let's suppose we've got an object moving in circular motion with a radius of r and a speed of v. So perhaps this is due to a bump in the road. Then our first step is always the free body diagram. This will begin always with the weight downwards, and then we look for other forces. In this case, we'd have a normal force pushing upwards from the surface. The key idea is that the net force has to be towards the center of the circle, which means mg has to be bigger than the normal force, which leads to our second step, which is to write the equation F net equals ma. So in this particular case, we've got mg minus n as the magnitude of the net force for that circular motion, or the centripetal force, and that has to equal to mv squared over r. And another way to write that is in terms of the period, where it's written as 4 pi squared mr divided by t squared. Or we can even write 4 pi squared mr times the frequency squared as the mass times acceleration. And now normally what you'll do is to isolate and solve for this normal force, or it could be a tension force, etc., and solve the problem. And that's all for today, folks. Thank you very much.